when it comes to adding vectors, there's a process for adding vectors. And the first thing I want you to know, ultimately adding and subtracting, it's the same process. Later in the year, we'll be doing some multiplication of vectors. That's a little bit more complicated in certain regards. But for adding and subtracting vectors, we're going to talk directly about a single process that we're going to do this on. And I want to start by giving you two vectors. We're going to use planes and airspeed versus ground speed as kind of our starting point, because it's easy to kind of understand. And there's some great videos that will show this off as well. So the idea here is that once a plane leaves the ground, it no longer has, it's no longer has an attachment to the ground. So its actual speed relative to the air is often different than its speed relative to the ground. And I use the word speed there wrong, so let me say it correctly. Its velocity relative to the air is different than its velocity relative to the ground, because very likely the air is moving. So if there's any wind at all, it's going to be adding to the velocity of the plane. So the plane might be pointed in one direction, but with the wind acting on the plane, it's actually moving in another direction. So let's consider a plane that is pointed itself in such a way that its airspeed indicates 120 meters per second relative to the air, and its heading is 30 degrees north of east. And to make this more about process than form, let's make the wind something easy. 30 meters per second, heading due north. So we're going to do this graphically first. And part of the reason is because my experience is that students are not necessarily well trained on how to use like their protractor and stuff. So I would like you to be capable people. So I want you to start by considering that if you do this graphically means just what it sounds like, that we're going to draw our answer out. And that requires that we draw this in such a way that we are being careful to make it to scale. So I'm going to start with a standard coordinate system that we are going to use to establish north, south, east, and west. I'm going to recognize that most all of this is taking place in the first quadrant. So I don't need the whole thing. I just need the part that's going to be in the first quadrant. And the way you add vectors together is by adding them tip to tail. Sorry, I got something in there I didn't want. Having a hard time getting this to do what I want to do. There, that's what I wanted. Okay. So we're going to have to come up with a scale. You'll have to come up with a scale. I will point out that in coming up with your scale, I made the wind speed a fourth of the plane's speed. So decide a size for the vector for your wind, and then 4 times that size will be the vector for your plane. Does that make sense? Now, we have to draw the plane so that it is traveling 30 degrees north of east. So we're going to draw the plane first, with the idea being that this is east and this is north. And that suggests a vector out in this direction somewhere. But we don't want it to just be out somewhere. We want to try and create a scale model of what's happening. So you have protractors out there, but there's usually 2 different kinds of protractors in the room. There's the kinds with the hole in it. How many of you have one of those? And then there's the kinds that just have a flat bottom, no hole. Who has one of those? All right, so they operate functionally similar, but they're not exactly the same. So I have one of each. So we will look at both. So I lay my protractor down so that the center is on the origin and my flat line is on the axis. And then I go to 30, make a mark. So there we go. Now the next part of this is you have to be careful. I am choosing my scale, and it's based on what I think is big enough for you to see. So my scale happens to be inches, and I'm going to go out 4 inches, or try to. So this represents 30 degrees and 120 meters per second. And this is the velocity of the plane. I assume you guys are doing the same. I'm going to move on to the wind here in a minute. Now, the wind is due north, but if you had something more complicated, you would need reference, because we're going to add the wind right to the tip of the plane. So it might be in your best interest to draw another quick coordinate system, especially if you had a wind that was more complicated. So I'm going to place my coordinate system so that it starts up right there at the end of the vector. And now I'm going to draw my wind, appropriate scale, which would be 1/4 of the size of the one I just drew, which means I'm going to draw it to be 1 inch long. So line up my ruler carefully. And there we go. I now have the wind, which is 30 meters per second due north. All good so far? Now your resultant is the combination of the plane's vector and the wind's vector. So for this problem, the resultant vector starts here, ends here. This is our answer. So this is going to represent the speed and direction the plane actually moved relative to the ground. Now I'm going to measure the length of the vector. Handy dandy ruler here. I get just over 4.5. It looks like it's 4 5/8 inches. I'll have to convert that to my scale. I also have to measure the angle. And for those of you who, again, new to using protractors, place my protractor down, make sure it's lined up correctly, make sure 90 is lined up, and I get what looks to be 42 degrees. And that's north of east. All right, we're almost done. We have kind of found our answer, but we need to convert our length into the appropriate units, which means taking what we had, our original ratio for our scale, and using it to find the length of the vector. So for me, that was 120 meters per second was 4 inches long. That has to equal my new length, which was 4 5/8 inches long. So I'll just cross multiply to get my answer here. And let's see, 5/8, 4 times 120 divided by 4. I get 139 meters per second. So this is my graphical answer. I don't know if it's close or not. We're going to work it out mathematically to see how close we are. Your graphical answer, regardless of the scale you chose, should be pretty close to this if you were careful about taking your measurements. We good to go on and do it for real, do the mathematical version? The mathematical version requires that you are going to do some sine, cosine, and tangent, so let's make sure that we have our calculators in degrees before we get started. And we're going to repeat the process, but I want to tell you that to do this mathematically, it's a 3-step process. Our math is only one-dimensional. So how do we add and subtract vectors? Well, we're talking about adding vectors right now. We'll talk about subtracting in a little bit. But adding vectors. Step 1, you have to convert all vectors to rectangular. Meaning you have to place your vectors in their component form. It's because we only have one-dimensional math. Once you've done this, you will add like vectors together. So add the x vectors together and the y vectors together. This produces your resultant vector. It produces the answer. The problem is that the answer is in rectangular. So to get a proper answer, you need to convert your resultant to polar. Now, look, a bunch of you don't need this spelled out to you, but I know some of you actually need more than just this. So what I would encourage you to do is consider making a simple chart. The top of that chart should have the component vector directions that you're going to use. I said before, I'm going to use x and y, so x hat and y hat. You can use I and j, whatever you feel comfortable doing. And then on this side, I'm going to list out my vectors. So I have a vector for a plane, and I have a vector for the wind. The plane is 120, 30 degrees north of east. And the wind is 30 meters per second to the north. So I just made myself a simple chart to help organize myself. So I put x and y on the top. I listed the vectors I'm going to be adding together along the side, and then I've placed what the size of the vectors are in place so I can use them. Now, one of these, I don't really have to do much work to convert, do I? That 30 meters per second due north really doesn't require very much. So I'm just going to write out what its vector relationship is, because there's 0 in the x direction and 30 in the y direction. That's that vector. Do I need to do anything more than that, or are you guys okay with that? I could draw a picture of it if you need to see it. We're all good? All right. So the other one, I think it's probably best if we have a picture. So here's our picture. The plane was flying 120 meters per second at an angle of 30 degrees north of east. We want to break this up into its components. Now, we did talk about this yesterday. I'm going to say out loud the things that I talked about yesterday. To break this up into components, the first thing I want you to do is wrap a triangle around the angle that represents the components. I'm going to wrap a triangle around the angle that represents the components. I will start by drawing a line that is adjacent to the angle that's drawing along the cardinal direction. Then, components have to be at a right angle to each other. So this has to be a right angle. So I drop down or slide over the other component vector to meet the first one on the coordinate axis. These are two different vectors, one in the x direction and one in the y direction. They represent the plane's velocity. It's how much of the plane's velocity is in the x direction and how much of the plane's velocity is in the y direction. So find out how much for each. That's the trig part. Timing starts now. That's about how long it should take. That's how proficient you should be. It should be about 30 seconds. But I'll give you a few minutes. So 60 and 103.9. Okay. So sine and cosine of 30. We had the hypotenuse. So that means our plane's actual vector in component form is 103.9 x hat plus 60 y hat. Alrighty, step one, done. Convert all vectors to rectangular. We have converted all vectors to rectangular. Step two, add like vectors. That literally means just add down the columns. So add all the x's together, add all the y's together. So adding the x's, I get 103.9 x hat. Adding the y's together, I get 90 y hat. This is the plane's ground speed in component form. So check. Now we have to convert this back to polar. That's its own process. So are we good to go? Now I always believe that it's best to do this with a little bit of graphical interpretation if you're new to this. So I'm going to do the same thing I did just a moment ago. My goal is to make sure that everybody can kind of watch as we work this out. So I'm going to draw another coordinate system to help make sure I don't screw this up. And the difference is I have the components now. I know that I'm supposed to go 103.9 in the x direction. Right? It's a set of instructions. And then I need to go 90 in the y direction. And these are the rectangular components that make up the vector for the plane. So the plane actually has a velocity that looks like that green line. And this is the angle it actually makes. I need to find r and theta. Now, again, just a little bit of trig, right? Judging by the angle that I'm working from, and like I said, you're supposed to select the angle of focus, but it's going to be told to you which angle to use. This is the opposite. This is the adjacent side. I'm looking for the resultant. I would probably use Pythagoras for the resultant, but I'll have to use trig for the angle. Again, I'll give you a second, and I'll tell you how long I expect this part to take. So this is where we're working from. All right. So that suggests the plane is making an angle of 41 degrees and is traveling at a speed of 137 meters per second. If I was to write out my answer, I'd have 137 meters per second at an angle of 41 degrees north of east. This is the plane's effective ground speed. No, not bad. I mean, we did it graphically. We got pretty close, or at least I got pretty close. We had 138 and 42 degrees. But the problem with graphical is that the thickness of your line and how you measure your lengths, all that makes a big difference. And small mistakes with your protractor usually translate into bigger mistakes too. So mathematically, not terrible, but I believe in thoroughness, and so I think you guys should practice. We have 12 minutes, so I think you guys could probably do one of these in less than 12 minutes. So here's what I'd like you to do. So a plane is flying at 220 meters per second relative to the air with a heading of 35 degrees west of south. The wind is to the west at 40 meters per second. Find the actual ground speed and heading of the plane relative to the ground. Yep.
Do you have to do this in both graphical and math?
No, let's just do the math part. As I look around the room, I'm going to set up a quick chart. 220 meters per second at an angle of 35 degrees west of south. And I want to break that up into x and y. And then I have 40 meters per second to the west. So I'm going to do the wind real quick because it's just along the x-axis. So it is negative 40 plus 0. All right, it is in the negative direction. So now let's consider the plane, because this is where I saw some troubles. If I was to draw the plane, well, I would probably have to start by considering what it means to be west of south. So start at the south, turn towards the west, 35 degrees. That's where the angle should be. Questions about that? This creates two components. This component is 180, and this component is 166, I think. Am I right? Or is it 181 and 166? What's that?
I got 166.
I have 166.
Well, let's see. I have a calculator here. This is going to be 220 cosine 35. That's 180 for sure. And my other one is going to be 220 sine 35. That's, I stand corrected, 126. Thank you. I think I jumped ahead to where I added my 40 in my head. So, negative 126 x hat minus 180 y hat. So I jumped ahead. 126 and 40, 166 x hat plus 180 y hat. Not plus, is it? Minus. So that gets us through step 2. Looks to me like I've got a vector this way. Well, let's see. That's 166. And this way, that's 180. You can do this in any order you'd like. So if you wanted to go 180 in the y direction first and 166 in the x direction, that's fine. But if I do it this way, the angle I'm going to be getting will be this angle. It's just all dependent on how you want to reference your final answer. So I believe the length comes out to be like, what, 244? We use Pythagorean theorem. So 244 meters per second. And this angle is going to come from the inverse tangent. So oh, I went the wrong way. Oops. Oh, well. Guess I'll do the whole thing because I forgot and I did bad. So I heard somebody say it out loud too. 47 degrees. So 47 degrees. And I have to give proper reference. This is starting facing west and turning towards the south. So I am south of west.